Thank you very much. It's a great pleasure to speak here. So I wanted to tell you about some recent joint work on the archive with Sam Gunningham. And this is about integrating symmetries of classical and quantum Hamiltonian systems. So let me kind of give the setting. So we're going to work over K, which is a characteristic zero field, which I like to call the complex numbers, and for today. And we're going to talk about a reductive. G is going to be a reductive group. So this means like complexification of a compact Lie group. So think, for example, SL2 or GLN or SPN, and so on. And I want to study Hamiltonian actions of the group G. And so what do I mean by a Hamiltonian action? I'll have two settings, kind of a classical and a quantum. So what's a classical Hamiltonian action? Maybe the main example is to just start with any space on which G acts. Take your favorite G. So I'm living in algebraic geometry, so I think of this as a G variety. And given a G variety, then you get, there's a symplectic manifold, the cotangent bundle of X. And the cotangent bundle of X carries an action of the group G, but the group action is a little bit stronger in that there's a map, the moment map. We have a map from cotangent bundle of X to the dual of the Lie algebra, which just at each point gives us the value for every element of the Lie algebra. We get a vector field on X. And this map is just describing those vector fields as linear functions on T star of X. OK, so we have a map from T star of X to G dual. And given any function on G dual, we can pull it back to T star of X and use it to generate a flow. And that will be the corresponding action of the Lie algebra. So it's an action of the group where the action of the Lie algebra is generated by Hamiltonian functions. More generally, we can have M could be any symplectic or Poisson variety, meaning that we have a map, functions on M. Any function on M gives rise to a vector field on M using the Poisson bracket. Every function gives a derivation of other functions. And we have the map, an action of the Lie algebra to vector fields, and we want to lift it to a map to functions. So that can be expressed as a moment map. So we have a map M. Maybe let's write it as a diagram like this. We have a map from M to G dual, which is encoding all of these functions, generating the Lie algebra action. And it's compatible with an action of the group. So you have an action of the group G on M, and an action and a map to G dual, which is equivariant for this coadjoint action. OK, so maybe I'd like to take also yet another perspective, is that you could just think of, given a map, you have a Poisson variety, you have a map to the dual of a Lie algebra. And so that gives a bunch of functions on M, so it gives a bunch of vector fields. And so you can ask for the problem of integrating these collection of vector fields to the action of a group. Okay. So that's kind of the perspective I want to take. So we have a map from M to G dual, and we wanted to integrate that. So let me kind of draw kind of a rough picture of what I have in mind. Here's my M. Here's my G. Can people see this picture? OK. So I have a map from M to G dual. On G dual, I have a bunch of symmetries, which are elements of the group acting, the coadjoint action of the group. And I want to take those symmetries and lift them to symmetries of M, okay, in a way that infinitesimally is described by this Hamiltonian flows. So that's this picture. So we look at the G dual and the collection of all the arrows given by the action of G. That collection is actually identified with the cotangent bundle of the group G. You can think of T star of G as an element of the group and an element of G dual. So T star of G is a groupoid. It's a collection of arrows acting on G dual composition. And we want to act this groupoid on M. So this is an example of what's called a symplectic groupoid. So T star of G is symplectic. And it's a groupoid in a compatible way. So it's a collection of arrows we can compose. This is just the action of G on G dual. And we want to lift this to an action of M. So this is belaboring maybe a simple point. This is how I want to think about a Hamiltonian G action. OK? Now I would like to talk about the quantum version. So what's the quantum version of all this? What's a quantum Hamiltonian G action? So again, let's the basic example. Let's start so let's take A to be an associative algebra. So for example, UG. And UG carries an action of the group G from the conjugation action of G on its Lie algebra. And you can think of this as giving a symmetry. Because the group acts on the Lie algebra, it acts on this algebra A, you get an action of the group G also on the collection of all modules for this algebra, which in this case is just representations of the Lie algebra. So given a representation of Lie algebra, you can move it to a different representation using conjugation by the group. Okay, so that's going to be an example of a quantum Hamiltonian G space. Another example would be to take again the same setup. You have any space on which G acts, and take A to be the algebra of differential operators on X. Okay. So if you look at the algebra of differential operators on X, well, if G acts on X, you get a map from the Lie algebra, or from the entire enveloping algebra, to A. This is the quantum analog of a moment map. Let me call it mu star. So we have a map from the enveloping algebra to A, to differential operators on X. And this map is equivariant for the action of the group. So that's the analog of the picture we have over there. Okay? So these are examples of what I mean by a quantum Hamiltonian G space. It's going to be an algebra, or if you prefer, a category, with an action of the group, which is Hamiltonian in the sense that it's generated by a map from the enveloping algebra. OK. So this is so again, to say it maybe in general, you have a group G acting. You have A as an associative algebra. And we have a map from G to A. And again, you could extend it to a map from UG, which is equivariant for an action, of the group G. OK, so so this is our setup. You can say this in this groupoid language if you prefer. Maybe you prefer not to. This is all a quantum Hamiltonian action is. You could say it in the so we could say this is equivalent to we can integrate the action. This is a map from UG to A to what's called a quantum groupoid, which is a fancy name for essentially a Hopf algebra, or really a Hopf algebroid. So this is the structure. What is a Hopf algebroid? If you look at functions on a groupoid, and you abstract the structure of the functions on a groupoid under multiplication and convolution, that gives you the definition of a Hopf algebroid. So instead of saying in the classical setting I had an actual space, T star G, an actual groupoid, and I can look at functions on it acting, here I can say it abstractly just in terms of algebraic object. In this case, the algebroid is literally just the differential operators on the group G. So differential operators on the group G have two maps from UG, left and right invariant operators, and you can ask for it to extend. So you can write a picture that looks a lot like that. Okay. I don't want to emphasize this. I don't know. If this makes you happy, this is good. You could say what a quantum version of a groupoid is. Or if you'd like, in geometric representation theory, we like to say this categorically. This is equivalent to an action of a monoidal category. Action of some category, which is modules for differential operators on G, acts on the category A mod. So if you think of non-commutative geometry as not being about algebras, but about their modules, you can say it in this language as well. OK. So, so these are the kinds of things that are studied in the local geometric languages program, categorical actions of groups. This is sort of where the motivation is coming from. There's also, I don't see a lot of physicists in the audience, so there's a motivation for this from supersymmetric gauge theory, but let me suppress that. OK, any questions about the setup? Obfuscating something very simple so far. Okay. All right, so now I want to talk about symmetries. So what do I mean by symmetries of these Hamiltonian actions? I want to take some operations that I can do on these classical and quantum operations, that spaces that commute with the G action. So where do I find symmetries? So given my Lie algebra, or little G dual, I have the characteristic polynomial map. So where does a characteristic polynomial, so these are the values of the characteristic polynomial, the coefficients of characteristic polynomial, or if you like, the invariant polynomials on the Lie algebra. So this lands in some space, let's call it C, which is, if you like, where just all invariant functions on the Lie algebra live. But this is identified by Chevalley. It looks like the dual of the Cartan, action of Cartan by Wahl group. So this is just a vector space. So there's a map, and this is just this is a vector space of dimension rank. This algebra looks like polynomials. It's just a polynomial ring in rank of G, many variables. So this is for GLN. This would just be trace and trace of the powers of the matrix. OK, so we have this characteristic polynomial map. Now, one thing that you can observe is that these ring of functions, these invariant polynomials, inside of all functions on G dual, they all are Poisson commute. They all Poisson commute. In fact, they're the center of the Poisson bracket here. So what does this give us? So remember, we had a Hamiltonian G space. We had a map from M to G dual. So we can compose it. We get a map from M to C. So what does this map from M to C give us? It gives us a bunch of functions. So this is a map to a vector space. So it's just a list of functions. And these functions, so this is L many Poisson commuting G invariant functions. So whenever I give you a Hamiltonian G space, I get a collection of rank many Poisson commuting invariant functions. So if you'd like, I get L many commuting flows. The corresponding vector field, I get a collection of commuting flows on any such space. And this is kind of the universal source of integrable systems. So integrable systems is a situation where you have the number is kind of maximal number of commuting flows. Here I'm not asking anything about the relation between L and the dimension of M. But I think most interesting examples of integrable systems come from this setup. OK, so now since these are G invariant commuting flows, since they're G invariant, you could say, well, I could have started with a G space, but now I can do any operation on this G space that commutes, that's part of the G action, and I'll still get these flows. They're invariant under the entire group G. So these flows, this whole structure descends to any Hamiltonian reductions, to any reduction of a G space, of a G space M. So for example, you could start with the kind of spaces that appeared, say, in Akshay's talk. You could take cotangent bundle of G mod K. This is a G space. Now you mod out by another group. I don't know if call it gamma or H, or depending on your. So you take things like this. These kind of spaces all carry this Poisson commuting flows. So these are an interesting collection of spaces that you get. They all carry the same collection in some sense of these commuting flows, because they were invariant under the group action. So if H and K are subgroups of G, you get this structure. OK, so this is an interesting collection of flows. Let's say the quantum version. The quantum version is maybe even more interesting and equally interesting. So the quantum version. So we had, again, this moment map. We have a map from enveloping algebra of G to A. Well, inside of there's the center. Given this algebra, it has a center. So again, we had, and the center, well, by definition, is a bunch of commuting elements in UG. And so we get a collection of elements in A that commute, but by construction are G invariant. So we get a collection. So again, this by Harishchandra isomorphism says that this is, again, the same polynomial algebra. Let me call them delta 1 up to delta L instead, to be more suggestive. But again, it's the same algebra of functions on the same space we had before. So the same algebra appears now, but appears now as a collection of G invariant commuting, let me call them differential operators. I mean, if A is indeed differential operators, so e.g. on a space like G mod K mod H for any two subgroups, you get collections of invariant commuting differential operators from this construction. And so this is kind of one of the main sources of quantum integrable systems. So these are the kind of Harishchandra higher analogs of the Laplace operator. OK, so what do you do with them? So there we looked at flows. Here you could look, for example, at the Harishchandra system, which you look at the common eigensystem. You look at the, let's call it, I don't know, m sub lambda, which is the eigensystem where you look at functions which are common eigenvalues, common eigenfunctions for all of these commuting operators. And you're very interested in understanding the behavior of these systems. OK, we're here lambda, and the parameter lives in the same space C. Again, this is this dual Cartan mod W. That's where eigenvalues of this commutative ring live. OK? That's right. I mean, they're G invariant differential operators up on G mod K, so they descend to differential operators on H, or more generally, any Hamiltonian reduction of G mod K. So you could do a Whittaker thing or something. Okay. So they live on any reduction, any two-sided reduction of G, for example, carries this big collection of commuting operators. OK, so that's a setup. So this is a classical and quantum system. Again, sometimes these will be integrable systems. Sometimes this is kind of a maximal collection of operators. Sometimes they're not. But yeah.
Why are you looking at proportions like this?
Why are you?
Why are you dividing on the left by 8? Why are you looking at this?
Why am I looking at these? Because these are.
Written on G mod K, you have it.
That's right. I'm saying there's a large class of spaces. So it's any locally symmetric space or any.
Asking what kind of H's are you dividing on the left? K.
Anything.
And why?
Well, I mean, maybe H is gamma.
I guess he's asking what.
Well,
maybe gamma.
H could be gamma, right? I mean, and then I'm not. Yeah. I mean, his H, I use H. His H has a different motivation. H could be gamma, and then you have. I'm not going to tell people here why. I mean, it's the Langlands program, among other things. But yeah, I mean, I don't know. This is the basic objects we get in representation theory of a group G. I don't know. Is that? Yeah, I mean, I guess maybe a less facetious answer is, when people construct integrable systems, classical integrable system, the Toda system, the Kolodra-Moser system, these systems are constructed exactly this way. You take cotangent bundle of G and you do some Hamiltonian reduction on the left and on the right by various subgroups.
Exciting integrable systems are ones where you don't start with a group, you discover remarkably integrable.
But you discovered that the group was there to begin with, even if you didn't know it.
Once you get the right code.
Absolutely. Right, but I mean, there's a lot of, so this is what Kostin's work in the 70s was focused on, is doing this in the case of the Toda system, for example, understanding where, once you understand the Toda system can be given this way, and then you can use all of representation theory.
Yeah.
Yeah. Right. OK, so yes, no, absolutely. So now, OK. So now I would like to understand how to take these classical and quantum systems and integrate them. So I want to understand how do you integrate these Hamiltonian systems, classically and quantumly. And so that's what the talk is about. So what do I mean by integrating it? So what do I mean by classical integration? Well, I have a bunch of commuting vector fields, and I want to find a group that acts, of which this is the Lie algebra. So I have this map to this vector space. And so I think of this as a bunch of Poisson commuting. This is a Poisson map. This is a bunch of Poisson commuting functions, or it gives a collection of commuting flows. And I want to find the problem of integration is look for a family of abelian groups, or if you'd like, a flat group scheme, over C. So a family of groups for each point in C, I'm going to give you a group which acts on fiber-wise on M, such that the Lie algebra, that's given the original flows. Does that make sense? So I have a bunch of vector fields. I want to integrate them. The group is going to depend on where you are in C. So it'll be a family of groups over the space that'll act on M, integrating these flows. OK. So if you'd like, you can think of this as another one of these symplectic groupoids, except that the two maps are equal. It's a family. It's literally a family of groups over a base. Nothing is moving along the base. OK. So it's so it's kind of analogous to what we had before, where we had the cotangent bundle of the group over G dual. Here, the two maps were left and right invariant projection. Here, the two maps are equal. So this is one thing I wanted to advertise. There's a fundamental construction of Ingo from the proof of the fundamental lemma, which gives, it's kind of a basic lemma in the proof of the fundamental lemma, which gives a universal solution to this problem. So in other words, for any of these spaces that we've mentioned, well, there's going to be a single family of groups, a single group scheme that acts on all of them, universally integrating these flows.
I think this was done earlier by Friedrich. No. We can discuss it.
OK. OK. OK, well, I'm not aware. So let's, but there's a basic construction here that, OK, well, we'll see. So there's a universal solution of this problem that given by Ingo. So how does this, what is his solution? So let me give a name. I guess I should be over, oops. Give a name to this J. He constructs this group scheme is called the group scheme of regular centralizers, one of the main topics of Kostan's work. This is the group scheme of regular centralizers. So what is the construction? So given an element x in G dual, I need to give you a group. Well, sorry, x. So I'm giving you an element lambda in C. I'm giving you a characteristic polynomial. So given a characteristic polynomial of a matrix, I need to give you a commutative group. So what is that group? So I'm going to pick an x with a characteristic polynomial lambda as generically as you can. So there are lots of different conjugacy classes with the same characteristic polynomial. Pick the most generic one you can, and look at the centralizer in the group of this x. So pick the best x you can, and look at its centralizer. If you don't like saying it this kind of fuzzy way, you can do this uniformly. Could take x to be the k of lambda, where this is the constant section. It's a particular section from a section of the adjoint quotient. OK. So that gives you kind of a canonical family of x. So this is a family of groups. So you take the best element. So let me try to illustrate this as best I can. So here's SL2. So here's my three-dimensional picture, supposed to be SL2. And then the space of invariant polynomials, there's just one, the determinant. So that's this map. So if you look at, so in SL2, there's really only kind of two possible values for the characteristic polynomial, non-zero and zero. So if you take a non-zero element, you take something with, so in other words, take a matrix with disjoint eigenvalues, then its centralizer in SL2 looks like a C star. So over a complement of 0, you have a bunch of C stars. So that's what this group scheme looks like. It's just C star everywhere. But at 0, you might have thought, to take a lift, you might have taken the 0 element. The 0 element in SL2 has a stabilizer to the entire group SL2, which is too big and not commutative. Instead, let's take an element which is, here's the nilpotent elements, take a generic nilpotent element. So in other words, take the element, so here's the constant section. You take an element q and take this companion matrix, 1q. You take a regular element with that characteristic polynomial, and you take its centralizer. And here, so in other words, instead of the 0 matrix, I'm taking this matrix, a regular nilpotent. And its centralizer is now, looks like C cross Z mod 2. So that's this family. You have a family of C star degenerating into this kind of C cross Z mod 2. That's what this group scheme J looks like for SL2. OK. So it's, if you want a formula, there's this not a particularly nice formula in general. For GLN, you could say that J sub, well, let me not write. You could write as J as the invertible functions on the spectrum of a matrix. Given a matrix, you look at its spectrum and look at all invertible functions on there. That's what this group is. In general, there isn't such a nice formula. So here's this. This is the constant section. It's a section of the map that misses the bad locus. OK, so Ingo showed. So this map was also in Knop. OK, great. So Ingo showed that there's a map for any element. So let me say it less formally. For any x in G dual, there's a canonical exists a canonical action of this J sub characteristic polynomial of X, there's a map to the centralizer in X. So in other words, to any element in Lie algebra, you can attach two groups. It's honest centralizer and it's regular centralizer. And there's a canonical map. And what is this map? It's defined in a kind of stupid or brilliant way. Most elements in the Lie algebra are regular. Away from a codimension 3 locus, this map is the identity. And then you just say Hartogs. So this map is just determined uniquely by what it does generically, which is just the identity. OK. For general groups, there isn't, as far as I know, a conceptual construction of this map. Go just says, use Hartogs. And this is going to be one of the things we're going to try to fight against, is try to find a better way of understanding what this map is.
Over 0, we go to the identity element.
Sorry?
Over 0.
Over 0, yeah. So SL2 is not exciting in that way, because the map at 0 looks stupid also, because it maps to 0. But if you take a higher rank group, then you do get interesting maps from this regular centralizer to the honest centralizer, which, again, if you think is this kind of functional calculus. Invertible functions on the spectrum of a matrix act commuting with that matrix. So that's the Ingo map for GLN. For other groups, I don't know of a.
So in terms of something like code that you do, and which many of my friends at NYU study,
yes.
What are you saying that's new from this point of view?
I mean, this is basically constant solution of the Toda system.
What did he say that was not known by like spares and sort of standard people who study Toda in finite dimension?
Well, he was able to give an explicit solution of the Toda system and the quantum Toda system for all groups, which I don't think was known. I mean, he actually described using Whittaker functions, give explicit descriptions of them. Of the quantum system. But even for the classical system, I'm not sure what. Well, yeah.
I mean, I guess for them, the infinite dimensions is the more interesting.
Sure.
With KDE.
Sure, yeah. OK.
I guess, and the Lax pair is this isospectral flow. That's this characteristic polynomial.
That's right. That's right. Yeah, so the nice thing about Toda is that you don't need to know about this Ingo map, because you'd miss it all lives over the regular locus to begin with, because there's some Whittaker thing going on. So you don't actually need the Ingo construction for that case. The Ingo construction will help you when you have. So as a corollary of this thing, you immediately get this statement I said, that this group scheme J integrates arbitrary Hamiltonian systems. And now where's the money in this? This is what Ingo used this. Applied this to the Hitchin system, slightly different formulation, but essentially the same construction to a Hitchin system. And there it's very crucial. You might have thought I have a bunch of commuting flows. I can try to integrate it by just somehow try to exponentiate. It's crucial that this group is disconnected. And it's really the connected components that appear that's where the phenomenon of endoscopy is captured by these groups of connected components, and use this as the fundamental symmetry principle behind the proof of the fundamental lemma. In the case of the Hitchin integrable system. OK. What do we do? So one of the things we want to do, this is one of the things we do with Sam, is we give a new construction. There's new construction of this Ingo action, which in some sense is much less explicit, but is much more structural. And we do it using kind of the best tool in geometric. We have a geometric representation theory. It's called the geometric Sasaki theorem, which is part of the geometric Langlands duality, which is really a kind of a non-abelian Fourier transform. So we translate the problem under a Fourier transform to a different situation. I'm not going to give a lot of details here. Just say we show that this map comes out of some very simple structural thing. Instead of looking at functions on this space J with its product, one thing you get out of this Fourier transform, in the GL1 case, this literally is a Fourier transform. You identify this with the equivariant homology of this space called the Affine-Grassmannian for the Langlands dual group. I don't know if I want to write. This is not crucial for anything. You look at the dual group over a Laurent series, and you look at double cosets for power series. So the main point, though, forget the details, is that it's a Fourier transform. The multiplication here becomes convolution here. So this is some Hecke algebra. This is an algebra of measures on double cosets, really homology double cosets, with a convolution product. So that's this multiplication. On the other hand, the coproduct, the group structure on this side, under the Fourier transform becomes something very simple. It becomes multiplication. That's what Fourier transform does for you. It becomes, well, here it becomes coproduct. Homology of a space has a natural coproduct, which is the coproduct, which is clearly commutative. So the commutativity of this group here is very evident here. And you can use this. So this is the kind of the basic realization. So I don't really want to belabor the proof, but the main point is that there's the geometric Sasaki theorem itself, or a form of it, says that the kind of the object you're interested in, quasi-coherent sheaves on the object you're interested in, get identified with some category of perverse sheaves, or derived category, equivalent derived category of this Grassmannian. And again, it's some tensor product gets taken to convolution. And then you apply some kind of abstract nonsense thing that you could say for any groupoid. So there's basic interaction that here you have convolution, and you have also tensor product of sheaves. And you just play between the interplay of tensor product and convolution gives you a map from modules for the homology modules canonically maps to the center of this. And this is some general nonsense you could say for whenever you have a groupoid. So it's just a version of, on the fact that n by n matrices, you have pointwise multiplication of kind of the stupid multiplication matrices, and you have matrix multiplication. And the interplay of those two gets some structure. So why am I, so out of this, you get a kind of abstract construction of the Ingo map, which doesn't use Hartogs. So maybe that's not so exciting if the Ingo map is pretty simple. So why do I want to say all of this?
Sorry,
yeah.
Ingo map, you mean the map?
This from regular centralizers to honest centralizers.
Could you give us an interesting example of that map where it's neither zero nor an isomorphism?
Yeah, I mean, take a matrix with, well, not for SL2, but I mean, if I take, so what is this map? I take a matrix, I look at its spectrum as a scheme, look at invertible functions on that, and then there's a map from invertible functions into the centralizer of any matrix with that spectrum. So if you take just you could do for SL3 or something, get a matrix that has two distinct eigenvalues, or yeah. So what is? Okay, that's the basic construction. So that construction is giving you an interesting map, as long as you have right. So for so the problem is that if you take the zero matrix, right, it's as the spectrum you get just. Sorry, it's about the difference between the minimal polynomial and the characteristic polynomial, right? So if you take a vector space as the module of your matrix, you get a sheaf on the spectrum. And if this sheaf is just supported at a point, you'll get the zero map as the action. But if the sheaf is supported, has bigger support on the spectrum, you'll get an interesting action.
So for SL3, but with only two distinct eigenvalues?
I think so, yeah. I can't do that on the spot, but yeah. And of course, where Ingo uses this is you have a map from a curve into this. You have a family of regular elements. And so these become some prim varieties of Hitchin fibers acting on the actual Hitchin fibers.
How do you get this map again?
Sorry, this, what, sorry?
How do you construct those maps?
Yeah, so this.
J above, actually.
Sorry?
J.
J was this group scheme. So we have this group scheme of regular centralizers. Yeah, so we have this J over C, that's this family of regular centralizers. So you look at functions on it. And the claim is that functions on it has a Fourier dual, Langland's dual description as homology, equivariant homology of the Grassmannian. So now, if I want to give an action of J on something, I can describe that in terms of, say, the category of sheaves on J. The category of sheaves on J, that's modules for functions on J. So that's modules for this homology. And just tautologically, there's an action of modules for the homology on the category of all sheaves. That's central with respect to convolution. Let me just write a little thing. Whenever I give you a groupoid, suppose I have a groupoid acting on a space X, okay? And take some set with a groupoid acting on it. Then you could look at the groupoid algebra. And you could look, let's take H to be the, the groupoid algebra. So measures, if you like, on this groupoid with convolution. And if you look at what is the category of modules for this groupoid algebra, kind of tautologically, it ends up being sheaves on X that are equivariant for the groupoid. Now, so the point is that modules for groupoid algebra always have a symmetric monoidal structure, because they're describing secretly sheaves on a space, equivariant sheaves. So this is trying to be sheaves on X mod G. So there's a symmetric monoidal structure, which might not have been evident before. And this always maps centrally to sheaves on the groupoid itself with respect to convolution. Whatever convolution is, it's linear with respect to X mod G. So that's the kind of two-line tautological proof. So once you put that in this situation and use geometric Sasaki, that gives the Ingo action. Let me move on, because there's something more interesting to say. So again, so far, let me try to take you guys back in. We went through a lot of heavy machinery to do something that was already kind of clear, at least if you like Hartogs. One of the nice things that we can do in this construction is you can quantize the Ingo action, which I think is something new. From this point of view, the quantization just means we're going to turn on equivariance for one extra parameter. We're going to have some C star equivariant version of all this. So we're just going to add a C star somewhere, which is just rotation on the Grassmannian. So we're going to do a version of this which is equivariant. So the abstract construction will look exactly the same. But now let me tell you what it's for. So now I want to say, what does it mean to quantize? So you can ask, what does it mean to quantize these Harish-Chandra Laplacians? What is it? To integrate a quantum Hamiltonian system. So that's the kind of question. How do you integrate these Harish-Chandra Laplacians? So what is it? What is the quantum version of the integration? So I want to propose that the quantum version of the integration, we're going to express symmetries. We're going to capture, let me say it kind of very informally, and give you an example, capture symmetry of the collection of eigensystems. So we have these commuting differential operators. We can look at their eigensystems. But there's a symmetry of the collection of eigensystems. In other words, if I give you an eigenfunction, if I tell you I have an eigenfunction for this collection of operators, it has a well-defined eigenvalue, of course. But the eigensystem doesn't have lambda as an invariant. Lambda is not an invariant of this eigensystem, in the sense that you can have isomorphic eigensystems for different eigenvalues. The system of differential equations can be conjugate. So let's give the obvious example. Let's take the group to be C star. Let's take our operator. This is this example of our operator. It's just the operator ZDDZ. And so we're looking at the Harish-Chandra system in this case. Just becomes the system ZDDZ minus lambda. We're just looking at lambda, just eigenfunctions of ZDDZ. Or if you'd like, you can think of the flat connection d minus lambda dz over z, flat connection on C star. And if you look at this system of equations, what you'll notice is that this system really depends not on lambda, but on lambda modulo translations. Or if you like, the invariant here is not this residue, but the monodromy, which is exponential of lambda, x of whatever, which is the monodromy. So that's the fundamental invariant. Lambda is not an invariant of the system. So what is this telling you about this system of equations? It's telling you that you should be adding some more operators. It's telling you that there's a larger algebra that acts where you adjoin to your differential operator. So we adjoin to our Harish-Chandra operator, which is the center of the enveloping algebra, which here is just polynomials in lambda, if you'd like. You adjoin the operators, let's call them sigma and sigma inverse, translate lambda. Right? So we have this translation symmetry here. And these operators intertwine the eigensystems. So the eigensystems, the collection of eigensystems is symmetric under these translation operators. So what do we get? We get an action of a bigger algebra. We get an action of polynomials in this one variable, adjoined sigma and sigma inverse, if you like the groupoid algebra of the integers. But by Fourier, or by the Mellon transform, this algebra really just is the algebra of differential operators on C star. This is just a isomorphic presentation of algebra of differential operators C star. So when we're saying we have a module for the algebra of differential operators in C star, we have two things. We have the action of lambda, but we also have the translation. Okay? So this is an example of this, if you like, one of these Hopf algebroids or quantum groupoids, just this algebra of differential operators. And so what we're saying is that it encodes the systems plus their translation symmetry. Now, of course, again, you didn't need me to tell you this for C star. The claim is that what we get is a non-abelian version of this. Right. So what do I call this integration? Because this algebra, I'm claiming that I'm getting an action of a Hopf algebroid, or quantum groupoid. The classical version of this, right? The classical version of this becomes exactly functions on T star of C star. So here we're looking at the, if you like, the integrable system, which is T star of C star mapping to C, projection on the cotangent coordinate. Here we know how to integrate that. Just fiber-wise, you just rotate by C star. So we have a function. So here it's a group. This T star of C star is a groupoid. It has multiplication. It also has fiber-wise multiplication, convolution. Now when we quantize, what happens? The base stays the same, but the functions on C, the group algebra of C star becomes identified with, functions on C star gets identified with the group algebra of Z, Cartier duality. So we get this algebra under quantization now becomes algebra of differential operators on C star. So what I claim is that, so classically it was clear what integration meant. You wanted to go from these Hamiltonian functions to an action of this groupoid. Quantumly, I claim there's an analogous thing. You want to go from these commuting operators to an action of the corresponding quantum groupoid, this Hopf algebra. And so the claim is that that you have such a thing. So the non-abelian version of this. So if I have A is a quantum Hamiltonian G space, again, you think of differential operators on an ordinary G space. Or its Hamiltonian reduction. So again, think of differential operators on G mod K mod H, for example. So whenever you have one of these guys, the claim is that the eigensystems for this action, these Harish-Chandra operators, the commuting operators, depend, let me say it first informally, depend not on lambda, the eigenvalue, which lived in this space, Cartan mod Val group, but they have an extra translation symmetry. So they depend on the class of lambda in a space which is Cartan modulo the affine Val group. So in the case of the abelian case, we're adding, so this looks like the Val group and a lattice. We're adding a lattice of translation. That's all we had in the abelian case. If you're not an algebraic geometer, you might say that this is you might identify C mod Z with analytically. You might identify this with C star, which is where the monodromy lives. Here, likewise, I'm going to give a group version of this in a second. But so the claim is that these Harish-Chandra systems have a different. Oh, maybe here's a picture of H star and H star mod W. Just I don't know. I'm not sure why. This is a phenomenon that's well known in representation theory. In representation theory, this appears in both as a theory of shift maps for integrable systems. This is an example of shift map. And the other example is translation function representation theory. If you look at representation of the Lie algebra, where you fix one value of the infinitesimal character, these are equivalent to category of representation of the Lie algebra, where you take that infinitesimal character and translate it, at least generically. So there's some extra symmetries between categories of representations of Lie algebras at different values of the central character. And that's what this action is going to be encoding. So it's a kind of a single algebraic action that's capturing all of these. So now let me try to say what the theorem is. So try to formulate the theorem. So the theorem, if you like, is that there's this universal, that the Ingo action quantizes to a universal quantization of all of these Hamiltonian systems. There's something that acts on any of these quantum G systems in a G-invariant way. So in other words, so there exists a commutative quantum groupoid So this is a co-commutative Hopf algebroid. It's an algebraic structure. That, and I'll spell out what this means in a second. Let's call it WH for Whittaker. And maybe I'll say why Whittaker later. There's a such that whenever we have these maps in the center of the enveloping algebra, these kind of things coming from the moment map to any of these quantum Hamiltonian G space or the reduction, this integrates an action of this Whittaker. So it's an algebraic object that acts in a way on all of these quantum G spaces in a way that if you take the classical limit becomes the Ingo action. So if you like, this is quantizing the action of J. Right. So for example, the differential operators on these double coset spaces. I don't actually like this language of groupoids as much as the language of categories. So let me say how you'd say this in categorical representation theory. Yeah. Yeah. So there's an object called WH. Let me write a formula. Well, OK, let me tell you what it is. Should I tell you what it is? OK, I won't tell you what it is yet. There's an object, which is a Hopf algebroid. Hopf algebroid just means it's a beast whose category of modules is symmetric monoidal. Monoidal, in this case, it'll be symmetric monoidal. It's a monoidal category with a forgetful functor to buy modules for this. But anyway, there's a Hopf algebroid over this ring. VG is the center of the enveloping algebra. There's an algebroid over the center of the enveloping algebra, which acts on A. So A could have been any of my quantum homogeneous G space. It acts in a way that commutes with the action of G.
What's it got to do with Whittaker?
Right. So it has to do because let me give you two formulas for what this WH is. So A, I guess I'm using A for two different things, but A could be any of these. So here I had UG mapped to A. I had a quantum Hamiltonian G space. One way I encoded a quantum Hamiltonian G space is that this, instead of saying it in terms of the more natural way, which is saying you have a group and its action on a moment map, you could have said it there's this Hopf algebroid, which is just differential operators on the group. And so you could just say there's an action of this Hopf algebroid on A. So the claim is that whenever you have such an A, there's an action of so here I have this differential operators in the group. There's a commuting action of this beast, this Whittaker beast, for any of these guys. So or if you prefer, I can do any reduction I want. So look at things like differential operators on a double coset space. And this guy still lives there because it's G invariant. Okay. So now what does it have to do with Whittaker? So this guy W is the Whittaker differential operators. It is differential operators on the group where you do Whittaker reduction. So you take upper triangular matrices and a non-degenerate character of the algebra of non-degenerate matrices, and you do Hamiltonian reduction on both sides. So it looks like differential operators on a double coset space, which is not quite a double coset space. So it's this algebra of Whittaker differential operators. And so the claim is that this is roughly acting on the center of G. Let me say this a little informally. It's going to some Drinfeld center of differential operators on G. And what is this supposed to remind you of? It's Constant proved this beautiful theorem that the center of the enveloping algebra, I guess we're just calling that ZG, the center of the enveloping algebra had a description. OK, so this guy lived over UG. So Constant proved that the center of the enveloping algebra was isomorphic to the Whittaker reduction of the enveloping algebra. This is a beautiful theorem of Constant's. You can describe the center of the enveloping algebra in terms of Whittaker as a Whittaker-Hecke algebra. And so what we're saying is that this is kind of an integration of Constant's theorem. Constant's theorem was about this enveloping algebra and its center. Now we're saying there's something about the entire group and its center. There's a Whittaker construction of the center of the group. This formula is of what WH is nice, but it's hard to work with. Let me give you the other formula, which is how we actually know anything about this guy. It's equivariant homology with respect to rotation of this Grassmannian for the Langland's dual group. here K is Laurent series. So this is a different description of the same beast. And again, there's two structures here. There's the multiplication from a double coset, and it has a coproduct because it's homology of the space.
How do you get from one of those to the other?
This is using geometric Sasaki. I should write the names. So I wrote their theorem. I should write their names. There's a version of geometric Sasaki, the derived geometric Sasaki of Bezrukavnikov and Finkelberg, which is kind of an enhanced which relates geometry of the affine Grassmannian to the representation theory of the Lie algebra or in Lie group.
There's a Whittaker, so I mean it's related to Whittaker. So
That's right. So the claim is that taking Whittaker vectors on one side corresponds to just taking cohomology on the other side. So, yeah. On the center, but let me put a z over this, right? Isomorphic. So the claim is that d of g is an algebroid over ug.
yes.
And this guy is an algebroid over this in kind of a tautological way. But the claim is that this is the center of it. These two maps, these maps are not equal anymore. And that's exactly the shift functor. So this is all to say what this algebra is. It's exactly the collection, just like in the Abelian case, we saw what this was. It's the commuting differential operators and some new operators, which are shift maps. So this is a structure which is exactly encoding all the shift maps, intertwining the eigensystems for different eigenvalues. And since that's my home base, let me just say the way we actually came to this and the way we like to think about it, the categorical statement, which in some sense is a little. So if you look at the category, let me do it curly H, which is modules for this beast. This has a very simple description. Well, at least this is a formula. It's sheaves on the Cartan modulo of the affine Val group. So that's where this identification. There's yet a third description of this Whittaker. OK, maybe that's too much to say. Anyway, this category has a description. It's just instead of looking at the usual representation theory, we think of living over the space of invariant polynomials. The claim is that these systems live not under the space of invariant polynomials, but are under their quotient by a lattice, under the space H star. And I'm using double to denote the coarse quotient, not some kind of stacky quotient, but the coarse quotient. So the claim is that this is a symmetric monoidal category. Well, saying it this way, I'm already giving away the symmetric monoidal. It's tensor product. Saying something as a Hecke category, Hecke categories are not usually symmetric monoidal. Hecke algebras are not usually commutative. Whittaker things are special. This guy is symmetric monoidal. So this is symmetric monoidal, and it maps to the center of sheaves on the group with convolution. And what that means in practice is it's a kind of a categorical version of the Harishchandra system. It means that whenever I give you, so let me just finish with this. So whenever I give you any G category, so whenever I have a G category, something like A mod, whenever I give you some G category, then it carries canonically an action of this Whittaker category commuting. So it's kind of it's a categorical version of commuting differential operators. There's a commutative algebra, categorical commutative algebra, which acts on any quantum Hamiltonian G space commute in a way that's invariant under G. Or you can take a reduction. So for example, if you could look at GK modules for any K, or you could look at systems of differential operators on any double coset space, say, these guys all carry actions of this, which means that you can give Langland's parameters. So that means that you can give a kind of, so let me just say that this means that you can give give a kind of Langland's parameters because this space analytically is the same as the dual Cartan torus modulo of the Weil group, which is the same as the affine quotient of the Langland's dual group. So we're saying that there's kind of functions on semi-simple conjugacy class or something. The affine quotient of the Langland's dual group acts on any G category. So these are kind of, so in other words, you can give, so this is a kind of a version of Langland's parameters for G categories. You can give them a point in here for a G category. And this is a version of the kind of a toy version of the local geometric Langland's corresponds. OK, thank you.